The moon is shrinking. The moon has been a constant companion to Earth, a beacon in the night sky that has shaped human culture, science, and imagination for centuries. It governs our tides, acted as a calendar for ancient civilizations, and motivated humanity to reach beyond our planet during the space race. But what if this ever-familiar object, seemingly eternal, is undergoing a quiet shift? Recent scientific discoveries reveal something extraordinary. The moon is shrinking. This isn't science fiction. It's a real phenomenon backed by evidence from seismic activity and surface features. In this episode, we'll explore what's causing the moon to contract, the evidence that supports this fascinating claim, and what it means for our understanding of planetary evolution. So buckle up as we embark on a journey to learn what our timeless cosmic neighbor is telling us about the dynamic forces shaping the universe. To understand how the moon could be shrinking, we need to start at the very beginning, its creation. Around 4.5 billion years ago, a Mars-sized celestial body, Theia, collided with the young Earth. The collision ejected a massive amount of debris, which eventually coalesced into what we now call the moon. At first, the moon was a fiery ball of magma, its surface churning with molten rock. Over billions of years, it began to cool. This cooling process set into motion the phenomenon of shrinkage that we see today. As molten material solidifies, it contracts, a process similar to how a grape shrivels into a raisin. But unlike a raisin, the moon's contraction has shaped its surface in ways that tell an incredible story. The most visible evidence of the moon's shrinkage lies in its landscape. NASA scientists studying the moon's surface have identified thousands of steep cliffs called lobate scarps. These scarps are essentially wrinkle-like features, formed as the moon's interior contracts and the crust is pushed together. Think of it as the moon's surface crumpling as its internal structure cools and shrinks. What makes this discovery even more fascinating is that these scarps are relatively small, just a few miles long, and some tens of feet high, meaning they formed after the moon matured. In planetary terms, they are geologically young, indicating that the shrinking isn't a relic from the moon's earliest days, but a process that is still ongoing. In addition to these scars, seismic activity on the moon, detected by instruments left behind during Apollo missions, provides further evidence of this phenomenon. Seismometers placed by astronauts recorded moonquakes, some of which were linked to the movement caused by the shrinking process. These quakes may seem subtle compared to Earth's tectonic activity, but they are critical in painting a picture of an active, evolving moon. The observations that led to this remarkable discovery wouldn't have been possible without NASA's lunar research efforts. The Apollo missions of the late 1960s and early 1970s were groundbreaking, not just for bringing astronauts to the moon, but for leaving behind valuable tools that would continue to collect data for years. In particular, the seismometers left on the lunar surface provided vital information. While they were initially used to detect meteorite impacts, they also recorded internal movements, moonquakes, that hinted at tectonic forces still at play. Decades later, when NASA's Lunar Reconnaissance Orbiter, LRO, began mapping the moon in exquisite detail, it revealed the widespread presence of lobate scarps. By comparing these findings, scientists connected the dots. The moon's shrinkage was causing these quakes and reshaping its surface. At the heart of this phenomenon is the moon's cooling interior. When the moon formed from molten debris, it contained enormous heat from its violent birth. Over billions of years, it has been gradually losing this heat into space. This cooling causes its once molten core to contract, and as the core shrinks, it pulls the overlying solid crust inward. The result? Lobate scarps, moonquakes, and a shrinking moon. But why does this matter? Understanding the moon's internal changes gives us insight into its evolution, helping scientists refine their models of how planetary bodies change over time. The moon is effectively a natural laboratory for studying these processes, offering a glimpse into the long-term cooling and contraction of terrestrial bodies across the solar system. The moon is not the only planetary body experiencing this phenomenon. Other objects in our solar system, like Mercury, also show signs of shrinking. By studying the moon, we learn not just about our closest neighbor, but about the broader mechanics of planetary contraction and tectonics in the universe. This raises some interesting questions. Will the moon's shrinkage ever stabilize? Could these changes impact its orbit or its role in stabilizing Earth's own rotation? Scientists believe the process is slow, far too slow to cause immediate concerns, but its implications could shape the Moon's distant future. One of the most striking revelations about the Moon's shrinkage is that it is still an active process. Moonquakes recorded by Apollo-era seismometers correlate with several lobate scarps, suggesting that the crust continues to shift. These quakes occur as the Moon adjusts to the stresses caused by its contraction. Unlike Earth's dramatic earthquakes, often caused by shifting tectonic plates, moonquakes occur due to thermal and tectonic forces. These tremors, though less intense, are vital clues that highlight the Moon as an active rather than static celestial body. This activity reshapes how we view the Moon, not merely as a relic of the past, but as a dynamic participant in the ongoing evolution of our solar system. As we come to terms with the idea of a shrinking Moon, many questions arise. How might this affect the Moon's surface in centuries or millennia to come? Will its tectonic activity grow stronger, or will it eventually fade as the core cools completely? Could the shrinkage alter its orbit, or have implications for the Earth-Moon system? For now, these remain open questions, but studying the Moon's shrinkage helps scientists refine their projections of its future and better understand the life cycles of planetary bodies. For example, scientists theorize that as the Moon continues to evolve, further surface changes could occur. Cracks may deepen, and regions may collapse under pressure. However, the current consensus is that these changes will happen on timescales far greater than a human lifetime and will not pose any direct threats to life on Earth. The shrinking Moon is more than just a scientific curiosity. It's a window into the universe's intricate processes. By studying its contraction, we gain a better understanding of celestial mechanics, planetary cooling, and tectonic evolution. These insights don't just apply to the Moon. They expand our knowledge of how other planets and moons across the galaxy may evolve over billions of years. From the discovery of moonquakes to the exploration of its ancient lobate scarps, our understanding of the Moon continues to grow. And with every revelation, we see our celestial neighbor not as a static, lifeless object, but as an evolving piece of the cosmic puzzle. The Moon's shrinking is a testament to the dynamic forces at play even in the most familiar corners of our solar system. It reminds us that nothing in the universe stands still, not even a body as ancient and immutable seeming as the Moon. Its evolving landscape is a powerful reminder of how much we still have to learn about the cosmos and how interconnected these discoveries are to our understanding of Earth and beyond. As we conclude this story, let the shrinking Moon inspire wonder at the quiet shifts that shape not just our celestial neighbors, but the universe at large. It is a story of motion, transformation, and the ever-changing tapestry of the cosmos.